In this video, I'm going to talk about something which is very basic but also very important, and that is the concept of a relation on a set. A relation is just a way of selecting out pairs of elements of a set that are related in some way. This is a very flexible notion, and there are a lot of things that you can do with it. But with a view towards some of the applications that we have in mind, I'm going to try to focus in pretty quickly on special types of relations called equivalence relations. We'll start with the definition, which is very simple. A relation R on a set S is just a subset of the Cartesian product S cross S. If an ordered pair of elements AB is an element of the relation R, then we denote this by writing ARB, and we say that A is related to B. It's also worth mentioning that there are lots of different notations for relations. Another common way of indicating that an ordered pair is an element of a relation is to write A tilde B, but there are other notations as well. For example, it's natural to denote certain relations by symbols such as less than or equal to or equal to. Which notation is most natural all depends on the kind of relation that we're trying to define. So we'll allow ourselves to be a little bit flexible with the notation in the examples that follow. What I'd like to do is build up a collection of examples of sets and relations, and then later on when we talk about what properties relations can have, we can come back to look at these examples to see which ones have the various properties. So for the first example, let's take the set consisting of the three elements 1, 2, and 3. To choose a relation on this set just means to choose a subset of the Cartesian product of S with itself. So we just need to go through and decide which of these 9 ordered pairs we want to take to make our relation. So for example, one relation could be the set consisting of 1, 2, and 2, 3. But of course, there are a lot of other possibilities as well. The biggest possible relation I could take on this set would be just to take the whole Cartesian product S cross S. There's not very many restrictions on the definition of relation. All of these are valid examples of relations on this set. A second example, if we start with a function f from a set x to itself, then we can define a relation R on the set x by taking the collection of all ordered pairs of the form x, f of x, where little x runs through x. This relation is called the graph of the function f. For our third example, let's suppose that we have a function f from a set x to a set y, and let's define a relation R on x by taking the collection of all ordered pairs x, x prime, where x and x prime are elements of x which satisfy f of x equals f of x prime. In other words, two elements of x are related to each other if the function f maps them to the same point in y. This is an important relation, and when elements x and x prime are related to each other in this way, we say that they lie in the same fiber of the function f. We'll come back to this example again later. For our fourth example, just to show the flexibility of this definition, let's let script t be the set of all triangles in the plane, and let's define a relation on the set script t by the rule that two triangles t1 and t2 are related to each other if and only if they're similar triangles. This is certainly a perfectly valid example of a relation on a set. For a fifth example, we could define a relation R on the set of real numbers by saying that two real numbers x and y are related to each other if and only if x is less than or equal to y. I hope that you're seeing from these examples that a relation is just a way of indicating a relationship between two elements of a given set. But the notion of how exactly that relationship is defined is very flexible. Finally, this is a very important example. And in fact, the next 2 videos are going to be devoted entirely to this example. Let n be a natural number, and let's define a relation on the set of integers by the rule that two integers a and b are related to each other if and only if their difference is divisible by n. To give a simple example, just to make sure that you understand the definition, when n is 2, the set determined by this relation is just the collection of all pairs of integers with the property that their difference is even. So for example, the set contains the numbers 0, 0, 0, negative 2, and 0, any other even number. And it also contains 1, 1, 1, negative 1, and 1, any odd number. And it also contains lots of other pairs of integers. The defining rule for being an element of this relation is that a pair of integers is an element of this relation if and only if their difference is divisible by 2. So another way to say that is that a pair of numbers is an element of this relation if and only if either both numbers are even or both numbers are odd. We'll come back to this and spend a lot of time talking about it, but for now I just want you to see the definition of this relation which of course depends on the choice of the natural number n. Now, there are a lot of different important properties that a relation R on a set S might satisfy, but we're going to focus just on 3. First of all, we say that a relation R is reflexive if every element of the set S is related to itself. So if XX is in R for all x's in S, then the relation R is reflexive. We say that it's symmetric if whenever xy is in the relation, we also have that yx is in the relation. And we say that it's transitive if whenever xy and yz are both in the relation for 3 elements x, y, and z in S, then it follows that xz is also in the relation. If all 3 of these properties are satisfied, then our relation R is what's called an equivalence relation. So just to make sure that we understand the definition, let's go back through and look at the examples that we've collected to decide which ones of those relations are reflexive, symmetric, or transitive. Let's start with our relations on the set with 3 elements. First, consider the relation R1 consisting of the ordered pairs 1, 2, and 2, 3. This relation is not reflexive because, for example, the ordered pair 1, 1 is not an element of R1. 2, 2, and 3, 3 are not elements of R1 either, but if even one of those pairs fails to be an element of R1, then the relation is not reflexive. It's not symmetric because, for example, 1, 2 is an element of the relation, but 2, 1 is not an element of the relation. And it's also not transitive because if we take x to be 1, y to be 2, and z to be 3, then both xy and yz are elements of R1, but xz is not an element of R1. Finally, since this relation is not reflexive, symmetric, or transitive, it's definitely not an example of an equivalence relation. Next, how about this relation? Well, first of all, because 1, 1, 2, 2, and 3, 3 are all elements of the relation, it is reflexive. And secondly, for every xy in the relation, yx is also in the relation, so it's also symmetric. And finally, since all of the elements of this relation have their 2 coordinates equal to each other, if you have 2 ordered pairs xy and yz in the relation, then x has to be equal to y and y has to be equal to z, which means that x is equal to z, and therefore xz is also an element of the relation. That shows that this relation is also transitive, so it's an example of an equivalence relation. In general, for any set S, if you define a relation R by taking the collection of all points of the form x, x, where x is an element of S, that's going to produce an equivalence relation. And since an equivalence relation is required to be reflexive, it's going to be the smallest possible equivalence relation on the set S. Now, at the other extreme, if we consider the relation S cross S, then since every possible element of the Cartesian product is in this relation, it automatically satisfies the conditions for being reflexive, symmetric, and transitive, so it also defines an equivalence relation on the set, and it's the largest possible equivalence relation that you can define on the set. Of course, this is going to be true for any set S, not just for the one with 3 elements that we're considering in this example. Going back to the relation R3 on this set, you can see right away that it's not reflexive because it doesn't contain the element 2, 2. However, this relation is symmetric since for every xy in the set, yx is also in the set. And it also turns out to be transitive. To quickly see why that's true, if you have 2 points xy and yz in this relation, then both x or z have to be 1 or 3. And since every possible combination of xz's like that is in R3, it means that the relation is transitive. Now, even though this relation was symmetric and transitive, because it was not reflexive, it's not an example of an equivalence relation. Now let's consider the graph of a function f from x to x, which remember was defined to be the relation R consisting of the collection of all ordered pairs of the form x, f of x, where x is an element of x. In order to be reflexive, this relation would have to contain all points of the form x, x. And the only way that that can happen is if f of x is equal to x for every x in x. If f is any other function, then the relation won't be reflexive. Now, is this relation going to be symmetric or transitive? Well, I don't know the answer, because it depends on exactly what this function f is. Depending on what you choose for the function, the relation may or may not be symmetric, and it may or may not be transitive. And that's all that we can really say in general. But as to the question of whether or not this is an equivalence relation, if it's reflexive, then it means that f of x is equal to x for every x in x, And that guarantees that the relation is also both symmetric and transitive, because in that case, the relation R is the smallest possible relation on X, consisting just of the points x, x for every x in X. So the answer here is that this relation is going to be an equivalence relation if and only if the function f has the property that f of x equals x for every x in X. Now let's look at our example where we bundled together all the fibers of a function f from x to y. So here the relation was that a pair of points x, x prime in X is in R if and only if f of x is equal to f of x prime. First of all, it's pretty clear, since for every point x in X, f of x equals f of x, that the ordered pairs x, x are all elements of this relation, so it is reflexive. Also, if xy is any element of this relation, then it means that f of x is equal to f of y. But then, since f of y is also equal to f of x, that guarantees that yx is also an element of the relation. Therefore, the relation is a symmetric relation. And finally, is the relation transitive? Well, let's suppose that I have a pair of ordered pairs, xy and yz, which are both in the relation. Since xy is in the relation, it means that f of x is equal to f of y. And since yz is in the relation, it means that f of y is equal to f of z. Therefore, f of x is equal to f of z, which guarantees that xz is in the relation. That's precisely the condition for being a transitive relation. And so here we have a very important example of an equivalence relation. Now, the relation of similar triangles in the plane turns out to also be an equivalence relation, but I'm going to skip the details of this one and instead move on to our example number 5. So here the set was the set of real numbers, and the relation was that x is related to y if and only if x is less than or equal to y. This relation is reflexive, since for every real number x, x is less than or equal to itself. It's also a transitive relation, since if you have three real numbers x, y, and z, and x is less than or equal to y and y is less than or equal to z, then it follows that x is less than or equal to z. However, this relation is not a symmetric relation, because, for example, 1 is less than or equal to 2, so the ordered pair 1, 2 is in the relation, but 2 is not less than or equal to 1, so 2, 1 is not in the relation. Therefore, this is not an example of an equivalence relation. And finally, one of our most important examples, let's look at our relation on the integers defined by a is related to b if and only if n divides a minus b. First of all, for any integer a minus a is 0, which of course is a multiple of any natural number n, and therefore n divides a minus a, so a is in the relation, which means it's a reflexive relation. Secondly, if a is related to b, then by definition it means that n divides a minus b. Well, that's the same as saying that there's an integer k with the property that a minus b is n times k. But of course that means that b minus a is n times negative k, so it implies that n divides b minus a, which means that b is related to a. And this relation is therefore a symmetric relation. Finally, to test for transitivity, let's suppose that a is related to b and that b is related to c. That means that a minus b and b minus c are multiples of n, so we can write a minus b as n times an integer k, and b minus c as n times an integer l. Then, if we write a minus c as a minus b plus b minus c, we find that a minus c is n times k minus l. In other words, n divides a minus c, so a is also related to c. This establishes that this relation is a transitive relation, and since it's reflexive, symmetric, and transitive, it's an equivalence relation. As I've already mentioned, this is an important equivalence relation, so it has a special notation to go along with it. If n is a natural number, and a and b are two integers, then we say that a equals b modulo n, if and only if a minus b is divisible by n. Now, one fundamental fact about equivalence relations is that when you have an equivalence relation on a set, it partitions the set into what are called equivalence classes. I'm going to define what a partition is later in the video, and then I'll prove that statement. But first of all, let's define what an equivalence class is. So suppose that tilde is an equivalence relation on a set S. For each element x of S, the equivalence class of x, which we'll denote by x bar, is defined to be the set of all y's in S with the property that x is related to y. So the equivalence class of an element is just the set of everything that's related to that element. And also, any element of that equivalence class is called a representative for the equivalence class. Before we look at examples, let me mention 3 facts that follow from these definitions. Remember here that we're assuming that we're working with an equivalence relation, and for every element x in S, the equivalence class of x is defined to be the set of all y's in S with the property that x is related to y. The first fact is that for every x in S, x is an element of the equivalence class of x. Of course, that's just the statement that x is related to itself, and it follows from the fact that any equivalence relation is reflexive. The second fact is that for any representative y in the equivalence class of x, the equivalence class of y is equal to the equivalence class of x. We'll prove this in 2 steps. First of all, by showing that x bar is a subset of y bar, and then by showing the reverse inclusion that y bar is a subset of x bar. So let's suppose that y is a representative for the equivalence class of x. Now what we want to show first is that any element of the equivalence class of x is also an element of the equivalence class of y. So suppose that z is an element of x bar, which remember means that x is related to z. Then since y is an element of x bar, we have that x is related to y, and because of the fact that every equivalence relation is symmetric, that also implies that y is related to x. But now, since y is related to x, and x is related to z, by the fact that any equivalence relation is also transitive, we also have that y is related to z, which qualifies z to be a member of the equivalence class of y. This shows that every element of x bar is also an element of y bar, so x bar is a subset of y bar. Notice also that in the course of proving these 2 facts so far, we've already used all of the defining properties of an equivalence relation. Okay, well, to prove the reverse inclusion, there's a little bit of a shortcut. Again, by the symmetric property, the fact that x is related to y means that y is related to x. And by the definition of y bar, that means that x is an element of y bar. Well, now we've switched the roles of x and y. And so if we just run through the same argument that we used in the first half of the proof, we come to the conclusion that y bar must also be a subset of x bar, which means that x bar is really equal to y bar, and therefore completes the proof. The third fact about equivalence classes is that anytime 2 equivalence classes intersect each other non-trivially, they must actually be equal to each other. Another way to say this is that when you have an equivalence relation on a set, distinct equivalence classes must be disjoint. This fact actually follows pretty easily from fact number 2, and the reason is that if there's an element y in the intersection of x1 bar and x2 bar, then applying fact number 2 to y and x1 bar gives that y bar is equal to x1 bar. But applying fact number 2 to y and x2 bar gives that y bar is equal to x2 bar. Therefore, x1 bar is actually equal to x2 bar. These 3 facts are pretty fundamental, and we'll use them again later. Let's go back now and look at some of our examples of equivalence relations to see what the equivalence classes are. First of all, consider the relation R2 on the set S shown here. What is the equivalence class of the element 1 of the set S? Well, since 1 is the only element of the set which is related to itself, the equivalence class of 1 is just the singleton set consisting of 1. And the story is similar for the equivalence class of 2 and the equivalence class of 3. In this case, the equivalence class of every element of the set is just the singleton set consisting of that element. This is what happens anytime you take the smallest possible relation on a set. You just get equivalence classes that consist of singleton sets. At the other extreme, if you take the largest possible relation on a set, then you're putting yourself in a situation where every element of the set is related to every other element. In other words, for every element x in S, the equivalence class of x, which by definition is the set of all y's in S that are related to x, is the entire set S. That means that there's only one distinct equivalence class, and it should be clear that this will happen for any set S if you take the relation to be all of S cross S. Now I want to look at our example from before where we had a function f from x to y, and we defined the relation R on x to be the collection of ordered pairs x, x prime with the property that f of x is equal to f of x prime. I want to try to explain more carefully what I meant when I talked about fibers before. So first of all, for every element little y in the range of this function, by definition there has to exist an x in the domain with the property that f of x is equal to y. Now let's write f inverse of y for the equivalence class of that element x. But I want you to be a little bit careful here, because there's a small clash of notation. F inverse here may not be the inverse function of f, because f may not even have an inverse function. It just happens that I'm using the same notation, but it's better here to call f inverse y the preimage of y, or the fiber over y. And that explains the language that I was using earlier when I talked about fibers. The fibers here are really the equivalence classes of elements in the domain. Now, if we apply our facts from before, we have a nice picture of how these fibers divide up the domain X. And there are two things to note about this. Number one is that every element of X is in one of these fibers, so that the domain X is the union over all elements of the range of the fibers above those elements. And number two, if we pick distinct points in the range and then consider the fibers above those points, they're always going to be disjoint. So the fibers break the set X up into all of these disjoint pieces, and there's one piece corresponding to every distinct point in the range. Now, I think you probably believe me about both of those points, but just for completeness, let's take a look at the proofs really quick. So first of all, the fact that X is the union of all the fibers is pretty easy to prove, because every element X in X is by definition an element of the fiber above f of X. This is really just a matter of looking at the definitions, and it follows immediately that X is the union of all of the fibers above the points in the range of the function. To prove the second claim here, that fibers above distinct points in the range are disjoint, let's suppose that I have two distinct points y and y prime in the range, that X is an element of the fiber above y, and that X prime is an element of the fiber above y prime. By definition, this just means that f of x is equal to y and that f of x prime is equal to y prime. But since y and y prime are distinct points in the range, it means that f of x is not equal to f of x prime, so x prime is not an element of the relation. Therefore, x prime is not an element of the fiber above x. And by almost the same argument, x is not an element of the fiber above x prime. Since no element of either set can be an element of the other set, that means that the two fibers are disjoint, and so we're finished with the proof. Now let's take a look at our final example, which is the integers modulo n. So if our equivalence relation is that two integers are equal to each other modulo n, if and only if n divides their difference, then what are the equivalence classes? Well, we can start by looking at the equivalence class of 0, and of course 0 is in there, together with all of the other multiples of n. Similarly, if you look at the equivalence class of 1, you get the set of all numbers of the form 1 plus a multiple of n. And continuing in this way, we can write down the equivalence classes for 2, 3, and so on, until we get down to the equivalence class of the integer n minus 1. The n equivalence classes in this example are also called the n residue classes of integers modulo n. And there are two main things to be aware of here. The first is that every integer is in one of these n residue classes. And the second is that all of these residue classes are disjoint. You may already be able to see why both of these are true, but there are a couple subtleties here, so I'd like to look at the proofs. The key to proving the first statement here, that every integer is in one of these n residue classes, is a result that we talked about in our video about properties of integers. And if you haven't guessed already, that result is the division algorithm. The division algorithm says that for any integer b, there exist integers q and r, such that b equals qn plus r, and r is greater than or equal to 0 and less than or equal to n minus 1. Well then, b minus r is a multiple of n, which means that b is equal to r modulo n, so that b is in the residue class r bar. Therefore, that establishes this first fact. Now, the second fact may seem kind of obvious to you because of what we called fact number 3 before about equivalence classes. That fact was the one that said that distinct equivalence classes have to be disjoint. But the real issue here is, how do we know that the equivalence classes in this list are distinct? Maybe two of them are actually equal to each other. Well, that's not going to happen, and to see why, let's suppose that I have r and r prime from 0 up to n minus 1, with r less than or equal to r prime, and let's suppose that r bar and r prime bar intersect non-trivially. Well, as we already said by fact 3 from before, that would imply that r bar is equal to r prime bar. But then the fact that r is an element of r prime bar would mean that r prime minus r is divisible by n. Now, since r and r prime are both between 0 and n minus 1, and r is less than or equal to r prime, we know that r prime minus r is greater than or equal to 0 and less than or equal to n minus 1. However, the only integer multiple of n in this range is the integer 0, so that forces r prime to be equal to r, and it completes the proof that these residue classes are in fact disjoint. You might have noticed a similarity in the last two examples. In both cases, we ended up with equivalence classes, which covered our set by disjoint pieces. Well, it's not going to come as a surprise at this point that that's not a coincidence. It's something which happens anytime you have an equivalence relation on a set. And in order to explain that, first of all, let me define what a partition of a set S is. If we have a set S and an indexing set capital I, and for each little I in I, we have a subset AI of our set S, then we say that the collection of sets AI with I running through I is a partition of S if three things hold. Number one, each one of the sets AI must be non-empty. Number two, S must be the union of all of these sets. And number three, the collection of sets AI must be a pairwise disjoint collection. Remember from our video about sets that for a collection of sets to be pairwise disjoint means that anytime you have two different indices I and j, the sets AI and AJ are disjoint. Now, the main things that I want to convince you of at the end of the video here are that number one, anytime you have a partition of a set, it can be used in a very natural way to define an equivalence relation on the set. And that, conversely, anytime you have an equivalence relation on a set, the equivalence classes form a partition of the set. Therefore, there's a close relationship between equivalence relations and partitions of a set. First of all, to understand how every partition of a set determines an equivalence relation on the set, let's suppose that I have a partition of a set S, and let's define a relation on the set by the rule that X is related to Y if and only if there exists an I in the indexing set with the property that X and Y are both elements of the set AI. Now, we claim that this is an equivalence relation on S. So first of all, let's check that it's reflexive. Any element of the set S is an element of one of the sets AI, and that's by property 2 in the definition of what it means for the collection of sets AI to be a partition of S. Well, since X is an element of AI, it's trivially true that both X and X are elements of AI, so X is related to itself, which means that this relation is a reflexive relation. Similarly, it's pretty easy to see that it's also a symmetric relation, because if X is related to Y, then X and Y are both in AI for some I, but then Y and X are also both in AI, so Y is related to X. Therefore, the relation is symmetric. To see why this relation is transitive, let's suppose that I have three elements x, y, and z of S, that X is related to Y and that Y is related to Z. By the definition of what it means for X to be related to Y, there has to be an I with the property that both X and Y are elements of the set AI. And by the definition of what it means for Y to be related to Z, there has to be a J with the property that Y and Z are both elements of AJ. But now notice that Y is an element of both of the sets AI and AJ. Since we're working with a partition here, by property number 3 in the definition of partition, that forces I to be equal to J. But if I is actually equal to J, then X and Z are both elements of the set AI, which means that X is related to Z. And that establishes the transitivity of this relation, therefore finishing the proof that it is in fact an equivalence relation. So this is what we mean when we say that every partition of a set determines an equivalence relation on the set. Finally, we want to prove that when we have an equivalence relation on a set, the equivalence classes determine a partition of the set. So let's suppose that we have an equivalence relation on a set, and let's let AI for I and I be the collection of distinct equivalence classes for this equivalence relation. Now, to show that this is a partition, we need to show three things. First of all, we need to show that each of these equivalence classes is non-empty, but that's pretty easy to do. First of all, each AI is x bar for some x in the set S, and by fact number 1 about equivalence classes from earlier in the video, we know that every element x of S is an element of the equivalence class that it determines. Therefore, the set AI is not empty, and that establishes the first property for being a partition. The second thing that we want to show is that S is the union of all of the AIs, but this is equally easy to do. Since each element of S is an element of the equivalence class that it determines, and since each equivalence class is one of the AIs, we're guaranteed that every element of S is an element of one of the AIs, so that the union is all of S. And finally, we want to show that the collection of equivalence classes is pairwise disjoint. So let's suppose that for two indices I and j, we have that AI intersect AJ is not the empty set. Well, since each one of these sets is an equivalence class of some element of the set S, by fact number 3 about equivalence classes, since they intersect non-trivially, we must have that they're equal to each other. It follows from this that if you have two different indices I and j, then the intersection of AI with AJ has to be the empty set, which is the same as saying that this collection of sets is pairwise disjoint. Now that we've established all three of these properties, we can conclude that the collection of equivalence classes is indeed a partition of the set S. This demonstrates the close relationship between equivalence classes determined by an equivalence relation and partitions of a set. That's the end of this video. Thank you for watching. In the next video, we're going to talk about how to impose a group structure on the collection of residue classes for integers modulo n.